The line consists of an infinite number of points. The plane of an infinite number of lines. The volume of an infinite number of planes. The hypervolume of an infinite number of volumes. No, not this. More infinite is decidedly not the best way to begin Borges's tale, nor this tale. Of course, we are not going to start this video with those infamous quotes by Mr. Feynman either. When people want to draw complex objects, they usually undergo art training that teaches them to methodically break those objects down into simple geometric forms. Much like classical art, mathematics offers many ways to break complex geometric objects down into simpler components. To apprehend those unspeakable geometric entities that lie far beyond the pitiful meat-bound cognition capacity of the human brain, mathematicians have developed a vast array of spatial structures to deconstruct these intimidating forms. For example, fiber bundle, foliation, cuberdism, CW complex, and handles. Morse theory, originally inspired by Maxwell's study of the topography of hills and valleys, provides an analytical method for decomposing geometric objects into CW complexes, favored in algebraic topology and instrumental in results such as Bott periodicity, and even explains why you can't comb the hair on a coconut. Or into handles, favored in geometric topology, which ultimately contributed to the proof of the generalized Poincaré conjecture. So what is Morse theory? Take a vertically standing torus smoothly parametrized as a surface. Now define a function h that simply measures height. There are 4 points on the torus where all the first derivatives vanish, which are called critical points. I have labeled them in green. Now watch the water climb up the torus and notice how the topology of sublevel changes. First, we get a disk. Then it becomes a tube. Then a punctured torus. And finally, the full torus. You can see that the critical points of H mark exactly the moments where the topology changes. Also, each critical point is assigned with an index which counting how many directions flow downward. We call height function HA Morse function. Formally speaking, at such a critical point, we compute the matrix of second partial derivatives, the Hessian matrix. If this matrix is non-singular, meaning its determinant is non-zero, then P is called a non-degenerate critical point. A smooth function whose critical points are all non-degenerate is called a Morse function. But what actually happens at a critical point? To understand it, we need the Morse lemma. Around any non-degenerate critical point P, there exist local coordinates in which the function looks like f equals fp minus some squares plus some squares. The minus squares count the downhill directions. That number is the index. We'll see this lemma again later in our physics course. And we've seen that topology changes at critical points. But what happens between critical points? Here's the first fundamental theorem of Morse theory. If there are no critical values between r and r plus epsilon, then nothing ever happens topologically. Topologically means we can naturally extend the size of epsilon. Therefore, the higher sublevel set simply deforms onto the lower one. In other words, between critical levels, the topology stays the same. As a consequence, Reeve's theorem tells us that no matter how strange a manifold may be, once if it admits a Morse function with exactly two critical points, one minimum and one maximum, then the manifold is topologically a sphere. One important application of this idea was John Milnor's discovery of exotic seven-dimensional spheres in 1956. I have made a separate video about that. You can find it on the channel. And now we are able to understand what actually happens at a critical point by using Morse lemma and the fundamental theorem. I will not give a full detailed proof, but I show usually how this is visually interpreted. Let's go back to the standing torus. As you can see, here's a valley ream where water would split directions. That point is a saddle. The second important theorem is crossing that saddle is exactly where the topology changes. So zoom this place in super close. Near a critical point, the surface looks like a standard quadratic shape and can consider as f of x and y is equal to x square minus y square. Now I add a slider E and look at. A of x and y is equal to x square minus y square plus e. What I'm really doing is shifting which height level I call 0. Now I switch to a top-down view so you can see the geometry without perspective tricks. In Milnor's proof, the neighborhood is split into 3 cases depending on which zone you're in. I'm going to compress those cases into one smooth motion. I can show you this change from to equally correct angles. If I color the points below the level, that's the set where f less than 0. This part. If I color the points above the level, that's f greater than 0. This part. Crossing E is equal to 0 makes one view look like things split and the other view look like things merge. But it's the same thing. It's just two sides of the same saddle. When E is on one side of 0, the region looks like one kind of shape. When E crosses 0, the shape changes. That jump is the handle attachment or cell attachment moment, whatever you called. They are equivalent here. So what is a cell? Basically, a 0 cell is just a point. A 1 cell is a line segment. A 2 cell is a disk. In general, a K-cell is the simplest possible geometric chunk of K-dimensional space, and it's especially favored in algebraic topology because it lets us build spaces in a structured, dimension-by-dimension way. Okay, now back to cell attachment. Mimic the part above the critical level, I also draw. C of x and y is equal to x square minus y square plus g multiples e. This function helps me isolate the part of the picture that will become the cell. In the original proof, the deformation retract is written piecewise. Case 1 here, case 2 here, case 3 there. I blend them into one smooth function. Wrapping function k that wraps c that c wraps a. When h is around 2, k is just approximation of c. When h is equal to 1, k is just a constant plane, totally flat. When h slides down, the square root shape gradually appears. Now the graph surface, it's like laying a sheet over the xy plane with height of a critical point. We can able to show the last deformation retraction then. I slide j toward 1. You see? The whole sheet gets squeezed in the y direction until it collapses onto a thin core. This is the punchline. The new piece you gained after crossing the saddle can be continuously shrunk onto its core. That's exactly what a cell attachment looks like in topology. You add a blob, but up to homotopy it behaves like adding a cell. In 2D, that core is basically a one cell, a line segment. In n dimensions, the same local quadratic model has lambda downhill directions and n lambda uphill directions, and the thing you attach is a lambda cell. So crossing one critical point adds exactly one cell of the right dimension. In physics, the action functional is often the first functional we ever meet. Instead of studying one path, we study all possible paths at once, and the action assigns a number to each path, like a cost or effort. Think about light choosing the quickest route or a particle choosing the path of least action. There are many nearby red paths that share the same start and end. But the green path where the action stops changing when you perturb them slightly. That condition gives the Euler-Lagrange equation, where the action S is the time integral of a Lagrangian along the path. Now let us switch viewpoint. Think of the path as a curve in space, not just a particle trajectory. We rename the path, call it gamma. In simplest case, there are no forces, no potentials. The Lagrangian depends only on speed. The extreme paths under circumstance are called geodesics. They are the straightest possible paths allowed by the space. If we now fix the endpoints and treat these geodesics as critical points, the action functional transitions to the energy functional. But not all critical points are equal. Some are stable, some are unstable. Among all geodesics, the shortest ones are special. They have no instability at all, and they form a whole continuous family. By applying Morse's spirit, we can study these geodesics by using index. The index counts how many independent perturbations decrease the energy. Index 0 means a true minimum. Higher index means more directions of instability. The index of a geodesy counts how many independent ways you can perturb it downhill, ways to decrease energy. 0 index means a true minimum. A large index means many directions of instability. But how do we compute these indexes? The secret lies in those arrows. They represent a Jacobi field, a tiny displacement along the geodesic with endpoints fixed. It describes how nearby geodesics separate or focus. Mathematically, Jacobi fields with fixed endpoints span the null space of the Hessian of the energy functional. That satisfies a Sturm, Liouville ordinary differential equation. This is the same type of equation that appears when you study the allowed vibration modes of a string with fixed ends. Not the full wave equation, because that's a PDE, but the part that determines when vibrations are allowed. So it's natural to think about a skipping rope. The longer the rope, the more ways it can vibrate. In geometry, the longer the geodesic, the more places these vibrations can vanish, and each such vanishing is called a conjugate point. If you want to turn this into Morse theory, energy acts like a height function on the space of paths. Energy controls length quadratically, so increasing the energy cutoff allows longer and longer geodesics. By Morse theory, each energy sublevel set of a space X is built by attaching one cell for each geodesic with energy below the cutoff C, and therefore has the homotopy type of a finite CW complex. More conjugate points mean more instability, and therefore a higher index. On a sphere, this instability grows in a very rigid way. If 2 points P and Q are not antipodal, there is exactly one shortest geodesic between them, and it has index 0. The next geodesic goes the long way around the sphere, passing through the antipodal point. Along that stretch, new Jacobi fields appear exactly n-1 of them. Go around the sphere again, and you pick up another n-1 directions of instability. So the indices grow like 0, n-1, 2 times n-1, 3 times n-1, and so on. Morse theory tells us that the space of all paths can be built step by attaching cells, whose dimensions are determined by the indices of geodesics. At special situations, like antipodal points on a sphere, instead of one minimal geodesic, we get a whole family of them. Bott realized that Morse theory still works in this case, as long as these families are clean enough. The cells don't disappear, they just become bundles over these families. For the sphere, the family of minimal geodesics from P to me P forms an S to N1. Everything else only appears in much higher dimensions. So, at low energies and low dimensions, the loop space looks like a sphere. Since the rest of the proof is admittedly tedious, I'm going to explain it in a tongue-in-cheek way to keep things interesting.
Listen, we must be absolutely clear. These insubstantial abstract nonsenses, these so-called light groups, they are the bourgeoisie of the mathematical world. They claim to be free, rotating and semi, rising however they please in multi-dimensional space. But I claim this freedom is a total ideological fantasy. It is built upon the exploitation of the point. The concrete laboring point whose individual toil is erased to support these lofty, airy abstractions. They float in midair, playing their language games of pure symmetry. It is the ultimate ideological fantasy of a space without friction. And so, the proletariat brings out its ultimate weapon, Riemannian metric. We are measuring the energy, the labor power of the task, and we find the index. This is not some smooth liberal democratic transition. No, the index grows in big jumps. It is a series of revolutionary ruptures. When we begin to calculate index of the geodesics, we are in effect conducting a class background check. On these arrogant structures, every time we weigh the variation of a geodesic, we are slapping handcuffs on these bourgeois structures. We no longer ask, how abstracted are you? No, we ask, what is your index? This index is their criminal record. Through this quantification, we drag these ethereal symmetries down from their pedestals and throw them into a high security prison called path space. And what is the role of Bott periodicity here? It is the prison management manual. It reveals that no matter how flashy these bourgeois structures acted in the outside world, the higher dimensions, once they are locked up, they exhibit a tedious, repetitive obedience. Unitary groups, every 2 floors, their behavior under reform is exactly the same. Orthogonal groups, every 8 floors, they start repeating the same confession letters, word for word. You see, this is the pinnacle of bureaucracy. Through measurement, we discover that these bourgeois have no individuality at all. They are merely prisoners of their own structure, repeating themselves in a rigid periodic cycle. But do not think this is the end. We arrive at the most brilliant part, reform through labor. This is just the intake. Later, and this is where it gets truly terrifying for the bourgeoisie, we will feed these periodic confession logs into the grand administrative machinery of topological K. That is where the sentencing happens. That is where we turn these prisoner profiles into a systematic organization of vector bundles. But first, they must sit in the cell. They must face the fact that their symmetry is just a 2-cycle or a name. Cycle loop of repetitive labor. Adam's theorem tells us that these incarcerated structures can no longer afford to be idle. We force them to work. We force them to organize vector bundles. This is their manual labor. When they try to lay down a smooth vector field on a sphere, they hit a brick wall. The Haribo theorem is the scene of their failed labor. They want to smoothly cover up the contradictions of the system, but the dialectics of mathematics forbids it. This failure proves that even the most elite bourgeois algebra must bow its head and plead guilty when confronted by the harsh reality of topology. Modern mathematics, it is everywhere covered in this sophisticated packaging, exactly like those corporate PR campaigns designed to mask the brutal essence of exploitation. But Bott's proof, it is naked, it is exposed, it is full of complex calculations of head-to-head bone, crunching geometric estimates.
The next major application of Morse theory is the proof of the generalized Poincaré conjecture. The claim is simple to say. In dimensions 5 and up, if a smooth closed manifold has the same overall shape as an insphere in the homotopy sense, then topologically it really is an insphere. The original strategy of Smale is called the Edge-cupboardism theorem. It's like this. Because of an insane magic trick in higher dimensions, if you can cut the target smooth manifold in high dimension into 3 pieces, 2 disks and a cylinder, namely an Edge-cupboardism, then the target manifold is homeomorphic to the n-dimensional sphere. But in higher dimension, we might encounter holes inside this H-cuberdism. What to do? Smale says, no need worry. He first proved any smooth manifold can be considered as a complex made of handles, which are basically thickened cells, a whole tower of handles. Then he applied some pure geometric magics to prove that, for an H-cuberdism coming from a sphere-like manifold in the simply connected high-dimensional case, all the handles can be cancelled out. So the scary-looking cuberdism is actually just a product cylinder, nothing hiding in the middle. In John Milnor's 1965 H-cuberdism lectures, Milnor adapted a different technique. Instead of pure geometric handle gymnastics, he showed us we can also perturb the Morse function so that we can cancel out critical points, and that yields the same effect as handle cancellation. We'll meet the reverse usage of this technique later and from the physicist's view. Smale wasn't only a topologist, he was also a dynamical systems expert. He introduced the concepts of gradient flow lines, stable and unstable manifolds, and the Morse-Smale condition into Morse theory, because he hoped Morse theory could also explain dynamical systems. If M has a Riemannian metric and f is a Morse function from m to the real numbers, then a gradient flow line is a curve that satisfies the differential equation, moves downhill as fast as possible. You can picture it like a particle sliding down the surface, always taking the direction of steepest descent. Or like a sticky ball that rolls downhill, but with so much friction that it never builds up speed, it just follows the gradient direction. Now, a Riemannian geometry 100 exercise. Prove the longitudes are the gradient flow lines on the round sphere for the height function. Hint: don't use the gradient definition from your Calculus 3 textbook or your calculation won't match. Then what are stable and unstable manifolds? Pick a point x and let gamma t be the downhill flow line starting there. It satisfies. D gamma polo gt equals minus grad f at gamma t with gamma 0 equals x. Flow lines usually end up at critical points. So pick a critical point A. The stable manifold of A is the set of starting points x whose flow line goes to A as time goes forward. The unstable manifold of A is the set of starting points x whose flow line goes to a if you run time backward. Stable means if you start there and flow forward, you end up at A. Unstable means if you rewind time, you end up at. Finally, the Morse-Smale condition. It says, for any two critical points, the unstable manifold of the first and the stable manifold of the second intersect transversely. Meaning, they cross cleanly, not overlap. Why do we care? Because then the flow lines connecting critical points are isolated. So later we can count them, and that counting becomes the boundary map in Morse homology. I will not go deep into the Morse-Smale condition right now, but here's an interesting case. Dynamic Systems 109. For a torus standing vertically under a height function, the stable and unstable manifolds do not satisfy the Morse-Smale condition. You just have to tilt the torus slightly to make it satisfy it. However, in the 70s, both the algebraic topology side and the dynamical systems side of Morse theory kind of hit a wall, for the same reason pointed out by Jurgen Moser, who worked in dynamics and PDEs. To really push Morse theory further, you want to use it on functionals, and that pushes you into infinite dimensional spaces, like Hilbert spaces, where functional analysis lives. But in infinite dimensions, geometry becomes weird. In an infinite dimensional Hilbert space, the sphere can deform into the disk, and it can even be contractible. So the usual sphere has non-trivial homology intuition breaks. So if you try to copy Morse theory into infinite dimensions, the topology stops giving useful information. Morse theory stayed quite until the 80s. Before that, I want to drop one early physics cameo I found from before the 80s. It's in the book Topology and Geometry for Physicists by Charles Nash and Siddharth Sen. This is solid-state physics in the normal sense. It's about crystals and phase transitions, basically condensed matter. My physics background is limited, so I can't explain what it says, but I'll leave the paper title here in case you want to look it up. Application of Morse theory to the symmetry breaking in the Landau theory of second-order phase transition by Louis Michel and Jan Mosrzymas. Before the final scene, I want to reveal two important inequalities. Yes, one more mathematical result to know. They are the bridge between Morse theory and the deeper algebra hidden inside geometry, cohomology. First is the weak Morse inequality. For each index k, the number of critical points of index k is at least the kth Betti number. This inequality is easy to see with a torus and a potato. For a torus, a simple height function has 1 index 0, 2 index 1, and 1 index 2 critical point exactly matching its Betti numbers 1, 2, 1. For a potato, a height function might have 1 index 0, 1 index 1, and 2 index 2 critical points, larger than the sphere's Betti numbers 1, 0, 1. Second is a stronger Morse inequality. If you take the alternating sum of critical points, it is at least the alternating sum of Betti numbers. So even after all possible cancellations, the remaining critical point data still cannot be smaller than what cohomology demands. The idea of the proof of the strong inequality is also surprisingly simple. From a Morse function, you can build a chain complex. We can keep the chain complex completely arbitrary here. What it really is doesn't matter yet, because it's not always easy to construct the geometric one when we need it. Ideally, we'd like to tie everything to Decomposition cohomology, since that's what differential geometers and physicists are most familiar with, but we can't justify that link at this stage. So for now, we just take the proof as a purely algebraic statement about an arbitrary chain complex. Its generators are critical points. So how many generators in degree k equals the number of index k critical points? And the homology of this complex matches the manifold's cohomology data. So homology in degree k equals the Betti number. In each degree, the generators split into 3 parts. The part that is immediately a boundary, the part that represents real homology, and the part that will become a boundary 1 degree lower. So the number of generators equals Betti number plus some extra pieces plus extra pieces from the previous degree. Those extra pieces are always non-negative and they always come in adjacent degrees. When you take an alternating sum, these adjacent extra pieces cancel each other out, except for one leftover non-negative chunk at the end. So the alternating sum of critical points cannot drop below the alternating sum of Betti numbers. That leftover chunk is exactly why the strong Morse inequality is always true.
Good day, gentlemen. This is a pre-recorded briefing made prior to your departure.
Supersymmetry is a hypothetical symmetry that links two kinds of particles. Force-carrying particles called bosons, like the photon, and matter particles called fermions, like the electron. It introduces an operator that transforms each boson into a hidden fermionic partner and vice versa, pairing them almost like mirror images. Because of this pairing, many complicated physical quantities simplify or even cancel out. Beyond its mathematical elegance, supersymmetry may help us help dark matter and make our quantum theories behave better at extremely high energies. Naturally, physicists want to ask whether this symmetry is broken or not. If supersymmetry were unbroken, bosons and fermions in each pair would have exactly the same mass. Let's quickly go through the basics of supersymmetry algebra. We consider a Hilbert space that splits into two parts, bosonic states and fermionic states. We write this as H equals H underscore B plus H underscore F. We introduce an operator called -1 to the F to distinguish two states. It acts like a parity switch, +1 on bosonic states and -1 on fermionic states. Supersymmetry introduces a special operator Q, called the supercharge. It is an odd operator, meaning it anticommutes with -1 to the F, so it flips bosons into fermions and fermions into bosons. Applying Q twice gives 0. Q squared equals 0. The same is true for Q dagger squared. The Hamiltonian is built from Q by the relation curly brace Q. Q dagger equals H. Equivalently, H equals QQ dagger plus Q dagger Q, so the energy is always non-negative. Finally, H commutes with Q and with Q dagger. So supersymmetry transformations preserve the energy of a state. Since Q squared equals 0, Q behaves exactly like a differential in algebraic topology. That means we can build a cohomology theory out of it. A state is called Q closed if Q applied to it is 0. A state is called Q exact if it can be written as Q of something else. Two states are considered equivalent if they differ by a Q exact piece. So, Q cohomology is Q closed states modulo Q exact states. And here is why physicists care. In supersymmetric systems, Q cohomology picks out the true ground states. All excited states come in boson-fermion pairs that cancel out in this cohomological sense, but the zero energy states survive. So instead of tracking the whole spectrum, we can study a smaller, more robust object, the Q cohomology. Does the Hilbert space actually contain a supersymmetric ground state, a state annihilated by the supercharges? In general, solving these equations directly is very difficult. So instead, physicists compute the Witten index. It is a signed count of supersymmetric states, with bosons contributing positively and fermions negatively. In other words, it is designed to detect whether supersymmetric ground states must exist. And if this index is non-zero, then supersymmetry must remain unbroken. The Witten index is powerful, but it is only one number. To really understand the supersymmetric ground states, we need the finer geometric structure behind that number. Naturally, we wish that Q cohomology should be closely related to the Derham cohomology of differential geometry. Edward Witten, in his seminal 1982 paper Supersymmetry and Morse Theory, made this relation precise. Let us identify the supercharge with the exterior derivative and its adjoint with the adjoint differential. With this identification, the Hamiltonian takes a geometric form. H equals 1/2 of the anticommutator of Q and Q dagger, which is 1/2 of the Laplacian. So in this model, the Hamiltonian is the Laplacian acting on differential forms. Its zero energy states are exactly the k-forms annihilated by the Laplacian. We call them harmonic forms. Hence, the supersymmetric ground states are precisely the harmonic forms. Now notice that d squared and d dagger squared both vanish. These operators naturally define cohomology, and cohomology classes generated in this way are isomorphic to Deram cohomology classes, which is good. We got what we want. However, the Laplacian form is too rigid to represent a finer supersymmetric Hamiltonian. Think of a sphere and a potato. Topologically, they are the same, but the potato has more critical points than the sphere. So now let us move to a more general supersymmetric Hamiltonian. We introduce a function h of x called the superpotential. The ordinary potential is built from its derivative. It is 1/2 of h prime of x squared. And the full supersymmetric Hamiltonian has three parts. First, 1/2 p squared. Second, 1/2 of h prime of x squared. And third, 1/2 h double prime of x times the fermionic term. So the bosonic part depends on the slope of h, while the fermionic part depends on its second derivative. Now consider the supersymmetric harmonic oscillator. If we choose h of x to be omega x squared over 2, then the Hamiltonian becomes the following. 1/2 p squared plus 1/2 omega squared x squared plus 1/2 omega times the fermionic term. Now we introduce a simple deformation. We replace h of x by t times h of x. Then the Hamiltonian changes accordingly. The potential term now scales like t squared times h prime of x squared. And the fermionic term scales like t times h double prime of x. As t becomes large, the potential term becomes very large away from the points where h prime of xi is equal to 0. So the low energy wave functions are forced to localize near these critical points. Near each critical point, we expand h to second order. Then locally, the Hamiltonian becomes approximately a supersymmetric harmonic oscillator again. Before that, let me clarify what the spectrum of the Hamiltonian is. In quantum mechanics, the Hamiltonian is the operator that measures energy. And a quantum state describes the wave of a particle. The Hamiltonian leaves the direction of certain special states unchanged. They are called eigenstates. Any quantum state can be built from these states. Each component evolves independently, oscillating with its own frequency. In fact, the Hamiltonian itself can be written as a sum over its energy states. This collection of energies is called the spectrum. This is why the deformation is useful. It forces localization, so the low energy spectrum becomes computable from the critical points. More precisely, each critical point gives a local candidate ground state. If h double prime at xi is positive, that local ground state is bosonic. If h double prime at xi is negative, it is fermionic. So after deformation, we can read off the low energy structure from local data near the critical points. And this is the basic idea that will later lead us to Morse theory. Finally, we are having a real geometric moment. Now choose a smooth real function, h on a two-dimensional Riemannian manifold, together with a real parameter t. Notice that this manifold is the space-time setting of the theory. Witten restricts the discussion to the simplest case, a world with one space and one time dimension, so that we are studying the simplest 1+1 dimensional supersymmetric sigma model. So in this setting, our space-time manifold could be a torus, a sphere, or even the surface of a potato. Witten now modifies the exterior derivative using this function h. He builds a deformed operator called d sub t by sandwiching d between exponential factors involving th. From this, we build a deformed supersymmetric Hamiltonian called h sub t. When we expand h sub t, something important appears. The old Laplacian is still there, but now we also get a large positive term. t squared times the norm squared of dh. There is also another term involving the Hessian of h, meaning the matrix of second derivatives. When t becomes very large, the term t squared times the norm squared of dh becomes huge almost everywhere. It only becomes 0 where dh is 0, namely at the critical points of h. So as t goes to infinity, the low-energy eigenfunctions are forced to gather near the critical points. This suggests we study how the eigenvalues behave when t becomes large. Write the nth eigenvalue, lambda kn of t, as t times a series, akn plus bkn over t plus ckn over t squared, and so on. The key question is this: which states have leading coefficient akn equal to 0? Because if the energy is really going to stay near 0, the leading order term cannot grow with t. So now we zoom in near one critical point. Near that point, we can choose local coordinates so that h looks approximately quadratic. In other words, h is equal to its value at the critical point plus 1/2 times a sum of lambda I times xi squared plus higher order terms. So locally, the deformed Hamiltonian becomes a supersymmetric harmonic oscillator with one copy in each coordinate direction. This local model can be solved explicitly. Its energy levels depend on two kinds of data. First, ordinary oscillator excitations. Second, fermionic sign choices coming from the differential form directions. The important point is that almost all of these local states have energy proportional to t. So when t becomes large, they are pushed far away from 0. Now restrict attention to k-forms. Then the fermionic signs are no longer arbitrary. Exactly k directions contribute with a plus sign, and the remaining n minus k directions contribute with a minus sign. For the energy to vanish, two things must happen. First, there can be no ordinary oscillator excitation at all. Second, the plus sign directions must line up exactly with the negative Hessian directions so that every contribution cancels. That means zero energy is possible only when k equals the number of negative Hessian eigenvalues. But that number is exactly the Morse index of the critical point. So each critical point contributes one distinguished local ground state, and it lives in the degree given by its Morse index. So low-energy supersymmetric states localize near critical points, and the degree of each surviving state is controlled by the Morse index. Comparing these ground states leads to the Morse inequalities. We have proved the weak Morse inequality. Hence, the number of perturbative ground states is always at least the number of exact ground states. So, in our 1 plus 1 supersymmetric nonlinear sigma model, supersymmetry remains unbroken. Moreover, through the relation between harmonic cohomology and theorem cohomology, we are already in a position to prove the strong Morse inequality. But Witten was not satisfied with stopping here. He wanted a physics explanation. After all, perturbation theory gives a candidate ground state near each critical point. But in the full theory, not every one of them remains a true ground state. In the full theory, these perturbative states can mix with one another. So what we really need to understand is the transition amplitude between them. Therefore, Witten introduces a concept called the instanton, where the supercharge Q is explained as a mechanism counting the number instantons between critical points. So what is an instanton? Let's start with tunneling. Consider the radial motion of an alpha particle inside a nucleus. The red curve is the potential energy. Inside the nucleus, there is a deep well. Outside, column repulsion creates a barrier. The horizontal line represents the total energy. Classically, the particle does not have enough energy to escape. But quantum mechanics changes the rule. As long as a potential barrier is not infinitely high and not infinitely wide, there is always a non-zero probability that a particle can penetrate through it. This phenomenon is called quantum tunneling. The wave function oscillates inside the nucleus. Under the barrier, it decays exponentially, but it does not vanish. Beyond the barrier, a small outgoing wave emerges. That outgoing probability flux is the escaping alpha particle. Traditionally, we analyze this using the WKB approximation. But now we switch perspective. Instead of real time, we rotate to Euclidean time. Under this rotation, the equations of motion change sign. The particle moves not in VR, but in the inverted potential minus V, R. The barrier becomes a valley. What was classically forbidden becomes classically allowed in imaginary time. The decaying wave under the barrier corresponds to a classical trajectory rolling across this inverted potential. That trajectory is the instanton. Its Euclidean action determines the tunneling probability. Quantum decay is classical motion in imaginary time. We now derive this picture directly from the path integral. In the path integral formulation, the transition amplitude between x_i and x_f is given by an integral over all trajectories connecting the two endpoints. Each trajectory is weighted by the exponential of I over h bar times the action. The Lorentzian action is the time integral of 1/2 x dot squared minus v of x. Among all paths, the classical trajectory is the stationary point of this action. This dominates the semi-classical approximation by stationary phase. To analyze tunneling phenomena, we perform a Wick rotation. We replace real-time t by minus I times tau. Under this transformation, the oscillatory weight becomes a decaying exponential. The factor e to the is becomes e to the minus se. The action becomes the Euclidean action. The Euclidean action equals the integral over tau of 1/2 x dot squared plus v of x. The sign in front of the potential term changes and the functional becomes positive definite. Now suppose the potential can be written as 1/2 times the squared norm of the gradient of a function, h. In other words, v of x equals 1/2 times the gradient of h squared. Then the Euclidean action becomes the integral over tau of 1/2 x dot squared plus 1/2 the gradient of h squared. We now complete the square. The Euclidean action equals the integral over tau of 1/2 times the quantity x dot plus gradient of h all squared, plus the difference h of xf minus h of xi. Since the squared term is non-negative, the Euclidean action is bounded below by the difference h of xf minus h of xi. Equality holds precisely when x dot equals minus the gradient of h. Therefore, the Euclidean classical solutions satisfy a first-order gradient flow equation. Such a trajectory is called an instanton. For an instanton solution, the squared term vanishes identically. The Euclidean action then reduces to h of b minus h of a. That is, the difference of the Morse function evaluated at the two endpoints. Thus, after Wick rotation, the dominant semi-classical contributions are gradient flow trajectories whose action equals the difference of the function h between critical points. We now turn to instantons in a supersymmetric setting. The bosonic tunneling path is still there, but now fermions are part of the story too. The Euclidean action now also contains fermionic terms coupled to the same background. To find the instanton itself, let us first focus only on the bosonic fields. The Euclidean action contains a kinetic term together with a potential built from the gradient of the Morse function h. So once again, the shape of h controls the tunneling behavior. Now we complete the square, just as in the ordinary instanton calculation. This shows that the minimum action paths satisfy a first-order equation rather than a second-order one. So the relevant trajectories are precisely gradient flow lines of h. The plus sign gives an instanton, while the minus sign gives an anti-instanton. And the corresponding action is simply the difference of the Morse function between the two endpoints. So in this supersymmetric setting, tunneling is again controlled by the geometry of the landscape. But now comes the genuinely supersymmetric part. Once the bosonic instanton background is fixed, we must also study the fermions fluctuating around it. This leads to the linearized fermion equations. Their zero modes will play a crucial role in the supersymmetric instanton calculation. Now we want to compute the tunneling amplitude. If we compute matrix elements of the Hamiltonian, we get two factors of the Euclidean action. So the amplitude is suppressed twice. But supersymmetry gives us a shortcut. Instead of attacking the Hamiltonian directly, we look at the supercharge. Then only one instanton factor appears. A non-zero contribution only happens when the two critical points differ by 1 in Morse index. So now the whole problem is reduced to summing over instanton paths between them. Each path comes with a coefficient determined by fluctuations around the classical solution. At this point, we can ask, how do we know how many such solutions there are? This is good and deep question because in my opinion, differential equations are always scary. I failed odd course twice back in my undergraduate career. If we keep digging, this road leads to some of the deepest mathematics of the 20th century and also to another great theory in physics. But we will stop here. We may not know every solution explicitly, but we can still extract one crucial piece of information, the index. This index measures the imbalance between zero modes. And because our matrix element contains one fermionic insertion, only instantons with exactly one unpaired zero mode can contribute. So the index tells us which instantons are even allowed to matter. Then we return to that coefficient attached to each instanton. For each isolated instanton, it is not continuous number but a sign. Two distinct instanton trajectories can connect the same pair of critical points, but if their orientations are opposite, one contributes positively and the other negatively, so they cancel. This means the supercharge acts by counting instantons between critical points of adjacent Morse index with sign. And that is exactly the Morse differential, and that is Morse homology or cohomology. From supersymmetric tunneling, we naturally get a chain complex built from critical points. So let's have a look how this is computed on a potato surface. On this potato-shaped surface, the supersymmetric differential Q is defined by counting instantons. Each critical point gives a state, but only some survive as true supersymmetric ground states. Start at D. There are two instantons from D to C, and they cancel. So, Q psi D equals 0. Thus, psi underscore D survives as a true ground state. Now move to C. One instanton goes to A and another goes to B. So Q psi underscore C equals psi underscore A plus psi underscore B. This does not give a new surviving ground state. At the top, A and B have no further upward flow. So Q psi underscore A equals 0 and Q psi underscore B equals 0. In the end, there is one surviving ground state at the bottom and one at the top. That is exactly the cohomology of SE2.
So at this point, we have already successfully proved that the strong Morse inequality by a physics method, And hence, on the physics side, we conclude that in the supersymmetric nonlinear stigma model, supersymmetry is never spontaneously broken if the space-time manifold has a non-zero Euler characteristic. Because of this project had went a bit of the closed control in the later stages, I couldn't finish the whole story, including bringing in the Morse Inequalities condition and fully building the chain complexes and so on. So in the last part of Witten's 82 paper, he proposed a sketch that tried to build an infinite-dimensional Morse theory for quantum field theory. Of course, he himself didn't necessarily make it, so because it's very, very hard. Later, it took Anders Floor 7 years to make this the idea work. The result is what we would call a Floor homology, a theory that does infinite dimensional space via a Morse type functional that's on an infinite dimensional manifold. We combine this with Hegel splitting in geometry topology, we call it Hegel Floor homology. And very recently, on January 13, 2026, Singalei, Jennifer Holm, and Ty Littman submitted an XV preprint claiming they detected the existence of countable infinite many exotic structures on 4-dimensional Euclidean space using Hegel floor homology. This is exactly what Gomph did about 40 years ago. If this is verified, then Hegel floor homology may become one of the most powerful tools we have to explore in the strange and chaotic world of 4-dimensional geometry.